there's a really cool video I found that talks about some of the history behind calculating pi. So if you click there, it'll take you to YouTube. You get to watch a Target ad.
We believe in the power.
Making money. Thanks, right. All right. Sorry.
This video is.
So these guys are pretty cool. I like this channel. So yeah. So you can watch that if you want to. It's really interesting. Gets into the history of how they calculated pi, blah blah blah, and then oh, it's so cool. There was some stuff in here that I really had heard very little about, especially about Pascal. I love Pascal's triangle. So if you don't know Pascal's triangle, it's in there. Anyway, so that's a very cool video. So that link is up here now in the Unit 7. What do you call it? Module. There we go. Okay. Now, also, oops, I should not have gone away from there. There's the practice. Let me see. Practice midterm is up here, right? So I need to make, yeah. Hopefully, read this the right way around. The practice midterm is about twice as long as the actual midterm is going to be, right? This thing came out to be, you should have seen it before I chopped this down. This is chopped down. So the actual midterm is not going to be this long because we only have as long as class goes to do the midterm. So it can't be that long. It's got to be very focused. What exactly is going to be on there? We'll find out together.
How does that work with other classes?
How do you mean?
Like other classes are like 2 hours and what, 15 minutes long?
Could
right?
be. Sure.
And their tests take longer, right?
It depends on the way the teacher wants to do it.
Okay.
Not every teacher makes tests that take the whole time. I was never one that could lecture and then give a test on at the end because I figure I'm not going to fry the brains of my students and then make them have to take a test. But everybody gets the same amount of time for the final exams, right? So that's one thing. And there have been classes I've taught, like 4-day-a-week classes where each class was 50 minutes. That's impossible. So I would do a test over the course of 2 days, like a test part 1 and a test part 2, because, 50 minutes, it's crazy to try to do a test in. All right. Anything else about that? Oh, what about people? Oh, that's a great question. Oh, you have got, okay. If you have accommodations with the ARC, you need to make an appointment to take it through the ARC. Right? I mean, quizzes are fine because they're not done during class time, but does that make sense?
Do that?
Well, if you filed your paperwork through them, then you just have to contact them and set up a time.
Okay.
Yep. Let me know if they give you any trouble because they've been saying they need a week, but that's insane. They shouldn't need that much time. There's less students at Grossmont. They should be able to work you in. So see if they can do that. Anything else about the midterm while it's a topic? Okay. So hopefully I'll get the solution video up. Good Lord, when am I going to do that? I have no idea. Obviously, hopefully before Thursday, that would probably be really good. Anything else, guys? Anything else from homework or general questions?
Wait, what day is the midterm on again?
What day is the midterm?
Thursday.
Thursday.
Okay,
Yes.
thank you.
You're welcome.
I'm excited for chapter 7.
Oh, well, that's good.
It's one of my favorite topics.
Thankfully, somebody said that. Yeah, I don't know. What have you guys heard? So we did get like the littlest bit into it. But obviously some of you guys have heard a bit about trigonometry, unit circle, that kind of stuff. Has anyone actually worked with that before? Yeah, a little bit or a decent amount. All right.
I accidentally did 3 classes of the trig.
Okay.
I I like had like anxiety for the first one, so it just didn't we just didn't connect. But like everything sort of still registered, so each time I took it, I just kept learning it better. I actually created like a whole binder just dedicated to study notes, and they were like rainbow colored. And
Okay.
so
Whatever gets you
I
through.
like the unit circle a lot. It's the graphing that's a little stressful.
Okay, understood. All right. And to me, trigonometry, it's astounding. It is, you got to listen to me. All right. It is at the same time a remarkably simple idea. You'll see. But the amount of stuff you can do with it is mind boggling, right? And there are a lot of cool animations showing you different connections between things. And, you've all seen sine waves and cosine waves, even if they weren't called that. Like an oscilloscope, when you see the frequency of a sound wave or something. Anyway, all right. So if there's no questions from homework stuff, we're going to get right back into chapter 7 where we left off. Okay. Oh, let me make it all about me. Hold on. Bow. There we go. Cool. So what we did last time, we barely got into the idea of a different way to define the angles in a circle. There had to be a better way because we completely made up one way, which is called degrees. They're completely made up. Right? They truly are. They have a bit of history to them. Why 360 is related to the length of a year. It's also mathematically convenient. You can factor in a lot of different ways. But beyond all that shit, it could have been anything. There could have been 2 degrees. There could have been 18 million degrees in a circle. It doesn't. There's no meaning to it beyond that. So we were like, there's got to be a better, more physical way to define angle measures in a circle. There must be. And that's where the idea of radians came from. They are a physical measurement, not just a made up unit. So just to remind us what we did last time. Get rid of my statistics. Get out of here. Let's see. See if I can. Is that better? Yeah, a little bit. So, circle. What we basically did. So I got as far as saying, if you take the radius, bend it, that would be 1 radian. We use the letter theta. This is the Greek letter theta. Right? So men who like trigonometry are theta males. Right? Nobody gets that? Okay. So the Greek, there we go. The Greek letter theta is one of the main symbols for angles, but it's definitely not the only one. Right? So this angle, if I put 1 radius curved onto the circle, this angle would be 1 radian. Okay. But in general, so what does that mean? What does that mean? What if I put 2 radii down? So what if I had a different, let me show you another symbol we could use. What if I put 2 radii down? So this is another radius amount here. What would this angle be? Let me use the symbol. Well, you might as well just go ahead and alpha. Right? Alpha is a little fish dude. All right, little fish dude. Okay, so these are letters we're going to see a lot of here in the near future. Let me see, I'm not really using my space well. There we go. What would that radian measure be? What do you think? If I put, this is an angle of 1 radian. What would alpha be in this picture?
Still 1 radian?
It can't be, no, careful. So see how alpha is this? It's not just here.
I see.
It's
Okay.
this, right? Otherwise, you'd be right. The angle that goes through here, that would be 1 radian. I agree with you. But this alpha goes from here to there. So what's the other person? What'd you say?
2 radians.
2 radians. Okay. That's all right. I understand both. 2 radians. All right. I really want this. Is that cool? Everybody, you guys with me? So it kind of makes, see what this is so much better. The angle is related to the distance that it goes through. But again, so let me see. Couple things. The general idea of what an angle measure is. Well, let me draw this picture again. Let me draw this picture a little bit differently. So what if I had radius and I have this general arc length? I don't know how far it goes. Arc length is S. So like here, the arc length is R, and here the arc length is 2R. You guys, everybody with me? So it's like a piece of the circumference. All right. Everybody with me? How would I figure out what this angle is? Let me use beta. How would I figure out how big that angle is if it's S and the radius is R? What do you think? Here the angle was 2. Why? Because 2 radians fit along here, right? So this is S. How would I figure out how many radii, right? How many radii fit along here? What would I do between these two things?
The ratio.
Yes. So beta would be S divided by R. Think about it. So that R divided by R is 1 radian. 2R divided by R is 2 radians. So any fractional piece in between, so maybe this will be 1/4 of a radian because it's 1/4 of a radius. So what does the angle actually tell us? How many radii, the number of radii that fit on the circle as I sweep through that angle? I really want that to make sense. So since if I sweep out through alpha, since 2 radii fit, alpha is 2 radians. Okay, maybe. Okay. Neat. Now let me erase all this. Start fresh. This is a big one. I'm going to rewrite that more generally. So now we know the angle measure in radians is the arc length divided by how big a radius is, right? So let me see. Gosh, I just forgot what I was going to do. Darn it. Oh yeah, there we go. Okay. So let's say let's do a concrete example real quick. So if I have this radius is 7 inches and I go, what do you got, Jeff? I go 3 inches. What angle is this? What angle have I just swung through?
3/7.
Yeah, 3/7 of a radian. Get out of there. All right, let me stop for a minute. Now, there will be several angles that we just have to know in radians. So right now, for example, if I ask you, all right, let's go to a general circle. Can you draw where 90 degrees would be? Can you make a 90-degree angle with this as one side? Of course you can, right? What do you do? So what would that be? How much of the circle have we gone through?
A quarter.
A quarter. Now, let's kind of build our way back to this, right? What is the circumference of this whole circle? What's the circumference of this whole circle? You can do this.
Pi r squared.
No, careful, that's the area.
360.
No, that's how many degrees there are.
2 pi r.
2 pi r. Okay, 2 pi r. So let's not forget the basic definition. Where did pi come from? It came from the circumference divided by the diameter. So C equals pi d. Diameter is twice the radius, so C equals 2 pi r. All right, let me stop for a minute. In calculus, you actually make the connection between, do you see how there's a 2 up there and it looks like the 2 just comes down? The connection, anyway, sorry, that's a little too far. I'll go back. So in calculus, you see a lot of those connections. You actually can see the connections through calculus between area and circumference and all this kind of stuff. It's so cool for a lot of different shapes. Anyway, okay, a little plug for calculus. So tell me this. What's the angle measure of the entire way around? How many radians total? I know there's 360. I don't give a shit. How many radians total are in this? Well, how far? What's S? If I go all the way around, what's S?
2 pi r.
2 pi r. So the angle would be 2 pi r divided by r. So it's 2 pi. There are 2 pi radians in a circle.
Professor,
Yes.
I missed what is d? Repeat.
Diameter. Diameter. Oh, you can't see diameter. Pretend like that says diameter.
Thank you.
You're welcome. All right, now we can right now connect what degrees and radians. We can right now develop a conversion between them. So now come at me. How many total degrees are there in a circle? I'll pretend like somebody just said it in chat. Okay, 360. And how many, so, and we just figured out how many total radians there are, right? 2 pi radians. So now if I divide by 2, 180 degrees is pi radians. That's the conversion between the two. All right, let me stop for a minute. So what's 90 degrees? What would 90 degrees be?
1/2 pi
Good.
rad.
Pi over 2 rad. Right, become a 2. Which is 1/4 of the way around the whole circle, right? Okay. So this will be pi, which is also 180 degrees. What would this be? What is it in degrees?
3/2 pi.
Okay, that's what it is in radians. Degrees is 270 degrees. And in radians, it kind of makes sense. You just keep adding pi over 2, pi over 2. You add another pi over 2, you get 3 pi over 2. Okay. So can somebody tell me 45 degrees? What would that be?
Pi over 4.
Pi over 4. Hello. You just got to cut pi over 2 in half again. I like it. Now, what about, so let me show you something kind of nifty that people sometimes miss. So I know this is true. 180 degrees is pi radians. Now, one thing you got to be careful about, if you just write, if I ask you how big is angle A and you write 7, that is assumed to be radians. Everybody listen to me. We're about to go into a whole chapter and the next few chapters where if you talk about degrees, you got to make it clear you're talking about degrees. If you talk about radians, all right. But if there's nothing, it's assumed to be radians. If you mean degrees, you better put degrees. I like it. Which one will we use more often? Probably the one that is actually a physical measurement, the radians, right? Most math people wishes degrees were never created. Okay. All right. So what if I have 60 degrees? How do you convert that to radians? Have you guys ever seen this neat little grid for conversions? You probably don't need this, but I want to show you this because it's a good tool for any conversions. If I want to go from degrees to radians, I want to kill degrees. Is everybody with me? I want degrees to go away. So where would you put degrees? On the top or the bottom? If you want them to cancel.
Bottom.
Bottom. So on the rads up top. So there's pi radians for every 180 degrees. So I'm just going to divide. The degrees goes away. Why is this legal? Well, isn't pi rads equal to 180? So what is pi rads divided by 180 degrees? 1. I can multiply anything I want to by 1, and that's all I'm doing. I just have to put the units in the right place so that they actually die. I don't want them up here so I get degrees squared. What the shit is degrees squared? Right? That's like Picasso trigonometry, square degrees. All right, that's a math and art joke, sorry. So of course, what does that come out to be? Just reduce it, don't give me no decimals.
1/3.
Yeah, so it's pi over 3. Now watch this. If I want to convert the other way, it's crazy easy. I don't have to do all this shit really. What's pi over 6 rads? How many degrees is that? Well, pi rads is how many degrees? 1/8. So I just have to replace pi rads with 180 degrees. That's 30 degrees. All right, let me stop for a minute. This is going to be an interesting journey we're going to go on, and I'm going to continuously be trying to get you used to the radians. So I want you to get to the point where you see this and you think this. So it's a lot like learning a foreign language. All of math is. When I see pi over 4, I think 45 degrees. I don't even think 45 degrees. I just think the idea of 45 degrees. Does that make any sense? I don't translate it, just know it. Ooh, Jeff, because I'm a math guy. What the shit, right? All right. Sort of like if I was born in France, I could do the French, but I can't do the French, even though I took 2 years of French. Oh, shit. Je vais à la plage. That's about all I remember. All right. God, too much shit. All right. So let's try a couple things. So I want you guys to take a minute and convert. And when you convert, you very often try to reduce. So let's see. So I want you to convert from one to the other. So like convert 135 degrees to radians. Convert 7 pi over 4 radians to degrees. And then how about convert? What do you got, Jeff? All right. 7 pi over 6 rad to degrees. All right, cool. Let's do those. I don't have any good trigonometry shirts. I was just realizing that. Oh well. All right, let me start to catch up to you. So this will be 135 degrees. I'm at 180 degrees to pi rad. And if you reduce these two, you should get
3/4.
good 3 to 4. So 3 pi over 4 rad. I like it. 7 pi over 4 rad. This is, so these two should be easy. Because pi radians is the same thing as 180 degrees. Right?
315 degrees.
Okay. 7 pi over 6 is 7 times 180 divided by 6. 6 goes into 180 30 times. So that makes 210 degrees. I like it. Now, real quick, let me ask you a question. Who remembers pi over 4? Pi over 4 was how many degrees by itself? Pi over 4. We did that earlier.
90.
5,
Careful, not 90. Pi over 2 is 90.
45.
Pi over 4, yes, 45. Now watch. Why does it make sense this is 3 pi over 4? Isn't? Stay with me, stay with me, stay with me. This is an idea we're going to come back to in a minute. How far away from 180 is 135? 135 is like right here. How far away from 180 is it? How far away is 135 from 180?
45.
45 degrees. You guys with me? Now stay with me, stay with me, stay with me. 180 is pi. Are you with me? Let me just extend that out. 180 is pi radians. So isn't this, wouldn't that be pi over 4 less than pi? I don't know. I really want you guys to see that, right? How would I get from pi back to here? I would have to subtract pi over 4 because that's what 45 degrees is pi over 4. What is a whole pi minus a fourth of a pi? 3/4 of a pi, right? Right? Okay. So since this angle is based on 45 degrees, it makes sense that the radian has a 4 on the bottom because pi over 4 is 45 degrees. So it's some multiple of 45 degrees. Okay, I don't know if you guys are all with me at all. Just trying to lay some groundwork right now. So same thing happened here, right? 315, what's 315? How far away from 360 is 315? Look at me having a purpose and a meaning to what I'm doing. It's crazy. How far away is 315 from 360? Just subtract them, right? 45 degrees. So this is 360 is 2 pi. This is 45 degrees back. So this would be 2 pi minus pi over 4. 8 pi over 4 minus pi over 4, 7 pi over 4. Holy shit, right? I really, really want you guys. Okay. And then this guy, well, let's see. What's pi over 6? That was 30 degrees. The way I remember these two, you see how they kind of go together? Pi over 6 is 30, pi over 3 is 60. That's awesome. So if you break pi by 6, it becomes a little tiny 30 degrees. If you break pi by 3, it becomes the bigger 60 degrees. So this is related to pi over 6. And sure enough, 210 is how much past 180? Is 30 degrees past 180, Jeff. 30 degrees more. So it's pi plus pi over 6, which is 7 pi over 6. Okay, I have no idea if you guys went with me on that journey. I know this is all very new, but I'm trying to point out interesting things about the results and why they make sense. And this is going to lead into stuff that we have to be able to do. Okay. All right. Okay. So let me get away from here. I'm going to erase all this. You ready? Here it goes. Somebody out there wants to say, please do erase all that, Jeff. Thank you so much. All right. Oh man. All right. So that's one idea, is the idea of radians and how they relate to the unfortunate degrees that already exists, right? So it's sort of like metric versus what we do here. All right. If only we only had radians, everything would be better. Sort of like metric. I'm sorry. So the next thing I want to talk about, the weird thing about circles is, so say I want to, get here. So I can go to, let's say this is 40 degrees. Okay. I want you to notice something. I went this way. So anytime I go counterclockwise. Yes. Okay. Counterclockwise. It's a positive number. What's another way to get, so if I want to get to that point right there, what's another way to get to it if I go this way? How many degrees is that? Let me see if somebody can get that.
320.
Yes, and since I went backwards, this would be negative 320. Negative just means you start at the origin, which is 0 degrees, which we kind of always do like this, and you go backwards. That's all that means. We call these two, negative 320 degrees and 40 degrees, we call them coterminal because they both terminate at the same place. Isn't that crazy? Coterminal. Okay, I like it. Not a big deal. But now watch this. Why don't they remove teaching degrees from the degree? Oh, okay. It's the same reason we don't go away from using metric, because it's too ingrained in all kinds of stuff, right? Okay. I mean, same reason we don't start using metric everywhere instead of inches and shit. What do you guys think about this? What if I said, what are you going to say, Jeff? I don't know, 510 degrees. What the hell would that mean? Where would I be? What's a coterminal angle that lives within our normal 360? What would 510 mean? 510 degrees. Physically, what would that mean? I turned and then I just kept going. How much more did I keep going? So I went 360 plus how much?
150.
150. I like it. So I'd actually end up at the same place as 150 degrees. Let me stop for a minute. Does that make sense? All right. So here, you guys do, what if I said negative 475 degrees? Find an angle between 0 and 360 that is coterminal with that.
$145.
Maybe. Let me see. Anybody agree? So I'm going backwards, right? So I'm rotating backwards some number of times. So if I take one full rotation off, I would add 360, but that gets me to negative 115, correct?
Yeah.
Then I've got to add 360 again. And that finally gets me to
145.
I like it. So it kind of makes sense. If I add 360 or subtract 360, that makes a coterminal angle because a 360 degree turn gets me back to where I was. It doesn't actually change where I am. right? Wherever I'm facing, if I turn by 360 either way, I'm facing the same direction.
So you can have a bunch of coterminals.
Definitely. Which really makes equations that kind of use circular reasoning, circular processing, really strange. Because you'll have, this is the whole idea behind trig functions, is they're called periodic functions. They keep having the same outputs over and over. They keep kind of repeating themselves forever. Sort of like a circle would. If I go around a circle, I keep seeing the same stuff. Look, kids, Big Ben, the Coliseum. I can't get off of this damn thing. I don't know. Sorry, that's a reference to an old movie. Some of you guys probably never saw it. National Lampoon's. Okay. All right, let me take all this away. So that's the idea of coterminal angles, right? And it brings into the the fray that I can go more than one turn at a time. So let me try to do this with, well, things get a little more interesting when I bring radians in. So let's try to, so here's 0. Here's pi over 2. So if I do this in radians, here's pi over 4. What would this one be? Big old clock. Sorry.
Pi 3/4.
Yeah, 3 pi over 4. And then, of course, a full pi. And then another quarter pi. And then another quarter pi, 6 pi over 4, which is 3 pi over 2. You guys with me? 6 pi over 4 plus pi over 4 is 7 pi over 4. That's the one we did earlier, remember? And then it would get me back to 2 pi. And then it would just keep going. And then it could also go backwards. This is also negative pi over 4, right? So with degrees, I can add, subtract 360 and end up in the same place, right? So one way to get a coterminal angle of 70 degrees is to add 360. So 430 is also the same thing as 70. These mean the same exact position, right? So how do I get a coterminal angle with like pi over 4? How do I get a coterminal angle? What would I add or subtract from it? Well, the equivalent of 360 degrees. What's equivalent to 360 degrees?
2 pi.
Okay. So if I add 2 pi to this, right, 8 pi over 4, so that'd be 9 pi over 4. So I'd go 2 pi plus pi over 4. So this is also 9 pi over 4. You guys doing okay out there? This is not something weird with radians, because degrees does the same thing. Because how many times can you go around in a circle for goddamn ever, and forever after that, and then forever after that, right? Okay.
You just get more and more dizzy.
Say again, sorry? More dizzy.
We'll just get more and more dizzy. Yeah.
More dizzy, exactly. Trust me, this stuff can make you dizzy very quickly. All right. Oh, I'm sorry. So some of these look like I'm sorry. All right. So now a slightly more important idea than coterminal. Slightly more important idea. Is the idea of reference angles. Jeff. Sort of got you ready for this idea earlier. A reference angle is just how far away from this line you are. So for example, if I go to the angle 115 degrees, how far away from this is it? So that it's the smallest distance between the x-axis and the angle itself, the terminal line itself. So what is this going to be?
75 degrees.
No,
60.
65. I like it. You guys get the idea that that's reference angle. So for example, let's try one in radians. What if I was at, oh, you can do it, Jeff. Can you do it, Jeff? Look at you doing it. All right. What if I was at 4 pi over 3? 4 pi over 3. Why do I know it's here? Because this is pi. So this is 1/3 of a pi. I just gave the answer away. But what would the reference angle here be? It's just how far apart those are. So how much past pi is 4 pi over 3?
Pi over 3.
Pi over 3. So this will be pi over 3 referencing. Now, real quick, do me a favor. Pi is how many degrees?
180.
180. Pi over 3 is how many degrees?
60.
60. And what would 4 pi over 3 be? That'd be 4 times 60, right? You guys with me? You guys with me? What's 180 plus 60? 240. All right. See, that's how far apart are those. So a reference angle will always be between 0 and 90 degrees, or 0 and pi over 2 radians. I really want that understood, because if I'm over here, let's say I'm at, what you got, Jeff? I don't know, man. Just don't know. Let's do 23/24 pi. I like it. No, Jeff. No, good try. Hold on. There. This is too much for you. Be quiet. Let's do 23/12. That'll do it. That'll do it. All right. 23/12 pi. The reference angle will be this. So it's always how far from this or this you are, whichever one's closer. That's the reference angle. So the actual math to find this shit is easy. Right now, you might be like, what the hell does this matter? We'll see soon enough, but right now it's good time to lay the groundwork. The math is relatively easy. How would I figure out what this is? Well, this is what?
1/12.
Yeah. So this will be 1 pi 12, 1 over 12 pi away from 24/12, which would be 2. Do you guys see that? So this is 1/12 of a pi away. So that would be the reference angle, would be pi over 12. Okay, I like it. I like it. So really, it's sort of like, so go ahead.
Is that just supplementing, or instead of saying supplementary angles or complementary angles?
Sort of, not really, sort of. Let me see, I'm trying to focus a little bit here. Let's see. That made it worse. All right. What am I trying to say? It's yeah, well, it sort of is, but it's not really, because it's like pi over 3 and 4 pi over 3 don't make 90 or something, or 180, right? We're talking about how do I say this? It's always either how much more or how much less than pi or 2 pi you are, right? So it's how much less than 2 pi I am, how much more or less than pi I am. If I'm in the first quadrant, which I'm pretty sure you guys know your quadrants, right? Quadrant 1, quadrant 2, quadrant 3, quadrant 4. If I'm in the first quadrant, the reference angles are the angles themselves, right? So if I was at, what do you got, Jeff? 17 degrees, the reference angle is 17 degrees. Oh, that's hard. So the first quadrant is easy. It's pretty much, they are their own reference angles. But the minute you get past 90 degrees or pi over 2, now you're referencing them with respect to this guy. So then they are sort of like supplementary angles. But then the minute you get past that, it sort of goes away from that idea. Do you see what I mean? So it's kind of related, but not true. All right, maybe. So let me see. Let me take this. This is getting a little messy. I've got a lot of problems up here. Let me take this away. So for example, if I had 5 pi over 4, I would hope that would be kind of easy. Can you just see how far past pi you are? How far past pi are you? You can make this into a mixed number, right? And then it'll tell you it's a whole pi plus how much of a pi?
Fourth.
Pi over 4. Yeah, so that would be the reference angle. Okay, so the reference angle is simply what's the angle measure between where you are and the closest you are to the x-axis. There's got to be a better way to say that. It's the shortest angle measure between where you are and the x-axis. That's what the reference angle is. Okay. All right, now. So this is all kind of laying groundwork. All of this is kind of laying groundwork. It would be great if we could get to something that we can put on top of this groundwork. So let's do that. All right, I got kind of a, yeah, good. I want to make sure I don't miss anything. I got a little outline of stuff that I want to go over. Oh, all right. So unfortunately, before we can get into the next level of things, let me come back. I got a couple things to do with, what do you call it? Arc length and stuff. So just to remind you guys, arc length has the letter S. And if you remember, the angle was S divided by R, right? That's how we figured out radian measure was to take how far we went divided by how big the radius is, because that would tell me how many radii fit there. Okay. That's how we defined radians. How you guys doing out there? All right. This actually, if I just solve this for S, I get the arc length formula. I get S is R theta. That's the arc length formula. This will only work if the angle is radians, because that's the only measure for an angle that is physical meaning. It has physical meaning to it. You put degrees here, it goes to shit. It doesn't mean anything. So if this is trying to tell me the actual length around the circle, I must use an angle that relates to that, and that's got to be radians. Okay. So now watch. So let's say, let's see, what do I say? Yeah, so let's say the radius is 45 meters, and I walk through an angle of, let's say I walk through an angle of, what do you got, Jeff? You can do it, buddy. Yeah, let's do 1.05 radians. So this is 45 meters is the radius, and I walk through 1.05 radians. How long is this? Right, so the angle measure is 1.05 radians, but how long is the arc length? How long did I walk?
Just multiply both.
So it'll be 45 meters times 1.05 radians. And you get whatever the hell you get. 45 point.
47.25.
Okay, thank you. Watts. This is where things get interesting. I love it.
Meters.
Meters. I love it. Now you could ask yourself, okay, stay with me. This is so cool, and I don't want to lose you guys. You guys doing all right out there? All right. Deal with me. You can say to yourself, okay, that's meters, but isn't that radians? So why isn't that meter radians or radian meters or something, correct? Would you be insane to say that? No, you wouldn't be. Not really, but that's not how this works. And here's why. The unit radians doesn't actually mean anything. It's a number of radii that fit across. So if I have an angle, and I know that this is 0.7 radians, that just means that 0.7 radii fit across that part of the circle. That's all it means. So it's like a number of. It doesn't, the units aren't really there. It's just a number of radii. Let me see. So, oh, that's perfect. So doesn't this mean that this is 1.05 radians? So wouldn't you replace radian with how long a radius is to see how far it goes? Let me say this again. Stay with me, guys. Stay with me. 1.05 radians means 1.05 radii lengths. That is what it means. So how long is that? Wouldn't that just be 1.05 times 45? Because each radius is 45 meters. That's actually another way to look at where the formula comes from. Okay. I feel like I've lost everybody. Damn it. It's a very, very simple idea. It's actually a different way to teach where the formula comes from. But if radian means the number of radii, then what does 1.05 radians means? 1.05 times 45, because it's 1.05 of these. Okay, maybe. So that's a very weird thing, that the radians units aren't really there. It's really freaky. They sort of get out of the way when I bring in other units, because it's actually a number of radii. It's not really a unit itself in the truest sense. Okay, maybe. Now, something else we can do with something like this, little pizza slice, is to find the area. So what about if I want to know the area and what we call the little pizza slice? So if I have a little pizza slice here, what we call this is a sector. So I call it a sector of the circle. This circle has seen better days. I think Tom Brady wanted to play soccer with this. There you go. Okay. Some more Deflategate. Okay. No. Okay. So I wanted the area of this slice of pizza. Now this is so cool. Stay with me. So let's say I know that the angle is theta. I know that this length, of course, is S. I know the radius is R. Right? Whoop-de-doo. Let me redraw this over here. What does it almost look like, especially if I do this? Yeah. What shape does that almost look like if I could just flatten one side of it?
A triangle.
Triangle. Okay. You ready? What would the area be if I do look at this as a triangle? Wouldn't the area be 1/2 the base times the height? Wouldn't it be 1/2? How long is this? Who remembers what the length of this is? What is the length of this? Not just S. I mean, what's the length of this?
R times S.
R theta. And then what's the height would be R, right? That is the actual formula, 1/2 R squared theta. That is the formula for the area of a sector. Now there's a slightly better way to get it. To be honest, once you get to calculus, if any of you guys get to calculus, ask your calculus teacher if they would please derive this equation for you using calculus. That's one of the first things I do. When we learn enough calculus, I come back to several things that you've done in your whole math career, and we show the easiest way to derive those things. Like the location of a vertex on a parabola. With calculus, it's stupid easy. Stupid easy. I mean, it took us for anyway. All right. Okay, so now we've got this area of a sector is 1/2 r squared theta. I like it. So, for example, let me see if you guys remember what I said earlier. What if I had a sector? Oh, geez, Jeff. Try a little bit better. There we go, buddy. And let's say that this is 50 degrees. And let's say the radius is 6 feet. I like it. Can you tell me the area of the sector? There is one thing you have to be careful about before you start throwing things in the equation.
Need to convert it to radians.
Yes, I love it. So this won't make all the sense in the world right now. But when the angle is out on its own, it's not so later we're going to learn these trig functions, sine of an angle, cosine of an angle, and all that shit. We're going to learn that probably starting tomorrow. If it's inside one of these guys, it could be whatever the hell units you want it to be. If it's out in the wild, if it's not inside of a function, if it's out in the wild, it has to be radians or it doesn't mean shit, right? So that's why we use radians. And here it could be degrees of radians, but here it's got to be radians. So why wouldn't you just use radians everywhere? Then you're covered. Your ass is covered. Yay. All right, so go ahead and do it. So she gave away one thing. You got to change that to radians, and then you can throw shit in, and then you get the answer. Well, that comes out nice. If you don't multiply the pi in there, well, even if you do.
So the answer is 5 pi.
Yeah, it comes out to be 6 1/3. Wait a minute. 36, 18, bam, 5 pi. 5 pi what?
Feet squared.
Good, square feet. So square feet, and the radians gets out the way. Square feet. And of course, if you want to approximate it, 5 times pi is roughly 15.6. 15.6 something. 15.66. I don't know. What is it? Anybody doing that for me? Nobody?
15.71.
71? Okay. All right. Q. All right, so little teaser for these things, right? So, I mean, the first section is just laying all the groundwork, which can be really boring. Oh, well. But the idea of radians, if it's the first time any of you guys have ever seen it, it is interesting. It is being more thoughtful about the units we use and how we get them, right? That makes more sense to use something based on the measurements of the circle itself instead of just, let's cut it up into 360 pieces. I mean, the shit. Why? Why? Doesn't make any sense. Okay, now, little teaser. Oh, shit. I probably erased that too soon. Sorry. So somehow we're going to connect the unit circle. The reason we call it the unit circle is because it's a circle of radius 1. Ooh, so 1, I don't know if you guys remember, you have prime numbers, you have composite numbers, and you have a unit number, which is 1. So that's why we call it the unit circle. It's not a circle that's really, it's a unit. No. It's the unit circle because it's got a radius of 1. Somehow we're going to connect that. In fact, I'm not even going to say somehow. I'm just going to show you. If I go to 45 degrees, doesn't that make a right triangle? In fact, probably before I can even say anything about sine and cosine, we really have to stop and talk about. So unfortunately, I'm not going to be able to say anything about sine and cosine tonight, I don't think. Can somebody tell me what the equation of this circle is? Does anyone know what the equation of this circle is? What it is? All right, now watch. All right, now watch. Let's say that's an x and that's a y. You guys with me? So there's the point xy. And it could have been anywhere. And this is a radius of 1, correct? So let me draw that again. This is 1, this is x, this is y. Can you give me a relationship between those?
1 equal y squared plus x squared.
Yep, good old Pythagorean theorem. That's the equation of the circle. Because every point on the circle is going to sit on its own triangle, isn't it? So here's another triangle, x, y, right? It's got to follow this formula. So what's the collection of every point on the circle are all the points that work in this equation? Okay, good. So maybe I did that quickly enough. That is going to come up a shitload. So we need to know what the equation of a circle is. Okay, now maybe I can sneak this in. Let's look at a specific angle up here. Let me make a bigger circle. Get out of here. Let me take this away. So we need this equation in general. You got to know this little equation. If the circle had a radius of 3, this would be 9, right? So in general, it's x squared plus y squared equals r squared. Still Pythagorean theorem, right? A squared plus b squared equals c squared. Okay. Now, last thing for today. If I have a unit circle, I am at 45 degrees. Let's do this in degrees for now. Why not? Right, so I've got this angle, this here. What's true about the x and the y piece at 45 degrees? What do you think? There's something special about 45 degrees.
They're the same.
They have to be the same. So let me redraw this up here a little bit bigger. Let me make it maybe look almost like it's supposed to be. Ah, screw it, Jeff. You suck. All right, my artistic talent leaves a hell of a lot to be desired. All right, buddy. It's okay, man. It's okay. You can do it. That's fine. All right. So this is supposed to be 1. Whatever this is the same amount. Okay, I like it. Now, can we figure out what those are? Of course we can, right? And this is for 45 degrees. So what would this angle be?
Also 45.
Also 45. Makes sense. The amount that this mouth opens is the same as the amount that this mouth opens. That's how I always like to think of it, right? I think of the Rancor from Star Wars, where he puts the thing in his mouth. Anyway, sorry. Major geeks things happen just now. How do I figure out this? I use freaking Pythagorean Theorem. X squared plus x squared equals 1. Go with me, right? Is everybody cool with that? So they have to be the same side length because these are both the same angles. So they have to have the same side length. That's Pythagorean Theorem. I did that a little fast, but I don't care. You guys could do it, right? I just solved for x plus or minus. Now, which one am I going to pick? Am I going to allow it to be plus or minus?
Probably not.
Yeah, I'm talking about side lengths of a triangle, right? So I'm not going to let the negative happen yet. Not yet. It's because we're in the first quadrant, correct? So x and y have to. So of course it's going to be different when we go to different quadrants. Right. And we do not appreciate radicals on the bottom. We do not. We want to rationalize those. How do I rationalize that denominator? I multiply what?
Square root of 2.
Square root of 2. Because that'll make the bottom become, no, Jeff. That'll make the bottom become a nice rational number. Let me stop for a minute. What the hell have we just figured out? Okay, what we just figured out is that, well, let me see. I shouldn't have done that. If I go to 45 degrees, the x piece and the y piece are both rad 2 over 2. Okay, so now watch. Does that really change if this was bigger?
No.
No, because well, let me be careful. It does change, but what doesn't change? So let me see.
The ratios don't change.
The ratios don't change. I don't want to redo the whole problem. Maybe I should. No, it's okay. So like, I shouldn't be trying to cram this in at the end, but I'm going to try to, just a little tiny bit. All trig functions is a realization of what we just said. For a given angle, the ratios of all the sides will be a set amount. I desperately want that. So let me deal with me. Let's say that I had a circle of radius. Just go with me. Hold on. Circle of radius 10. The radius is 10. So this is 10 there, right? So then I do this whole problem again with 10, x, just watch. You don't try to write. So I do the whole thing again, x squared plus x squared equals 10, 2x squared equals 10, x squared equals 5, x is plus or minus, we already know it's not the negative, x is square root of 5. I did that really fast. Okay, I think that's right. So this is square root of 5, this is square root of 5. Now, what's the ratio of this side to this side is rad 2 over 2. You agree with me? Of course, rad 2 over 2 divided by 1 is rad 2 over 2. Wow, right? So I'm going to say the x side divided by the radius is rad 2 over 2. What happens down here if I take the x side divided by the radius? What do I get down here? You can do it, Jeff. So what's the x side divided by the radius? It's just going to be rad 5 over 10. Now watch what I can do. I feel like no, everything's right? Yeah. I feel like it's wrong, but it should be fine. Yeah, it should be. Oh, I see what I did. No, okay. I think it's okay. Yeah, okay. So if I multiply this by,
Doesn't it have to be 100?
oh, that's what it is. Oh, thank you. Good Lord, I'm going crazy up here. This is what happens when you try to go so quickly. Oh man, all right. So that should have been 10 squared, 100. I should learn my lesson and not try to do this so quickly, but oh well. So that would make this, x would be square root of 50, which I can write as square root of 25 is 5. All right, let me stop for a second. Right, so that should have been 100. Thank you, because it's x squared plus y squared equals r squared. 100 divided by 2 is 50. Square root of 50 is square root of 25 times square root of 2, so it's 5 square root of 2. That's why I felt wrong. Good Lord. Now, if I take, so the ratio of this to this is rad 2 over 2. What's the ratio of this to this? 5 rad 2 over 10 is still rad 2 over 2. It kind of makes sense because however bigger or smaller the triangle is, every side is multiplied by the same thing. So when I take a ratio, those cancel. It comes back to a standard amount. So I want to create a function that tells me for a given angle, what's the ratio of this side to this side. And we actually call that function the cosine. We just give it a name. Because so all the cosine function does is it tells me the ratio for a given angle, what's the ratio of the x side to the hypotenuse. That's all it does. That's it. So there are 6 trig functions. The ratio of this side to this side, the ratio of this side to this side, and the ratio of this side to this side. And then there's so there's 3, and then there's the reciprocal functions, the other way around. Right, so and then it would be this side, it's just the other way around. So that's why there's 6 total trig. But what do they all tell you? The ratio of the sides of triangles. That's all they tell you. How much can you do with them? An insane amount. Okay, I'm very sorry. I tried to do too much there at the end. I think that's plenty. So we definitely finished section 7.1. We took a little peek at 7.2. Right. And hopefully I'll get the answer key for the practice midterm up tomorrow. I think I should have time tomorrow. And then Wednesday we'll probably devote at least a chunk of class to reviewing for the midterm the next day. All right. I thought I was tired before. So that's it. Let me know if you need to hang out. Otherwise, you're free to go.
I gotta hang out.
All right.
Have a really good one.
Take care, man.
Thank you.
Sure. Oh, what'd you have, Jordan? What was that?
I was just showing you my notes.
Oh, Anita.
It goes over like all the cosine stuff. It's in rainbow. You can see the different things.
Coolness.
I just have like, it's all cut up from my old trig notes. So I have like chapter 1 and like we did like vocabulary with it, and
Okay.
it's just nice to have.
Yeah, totally. I'm sure everybody else would like send that to Kinko's and send it out to everybody.
Yeah, totally. All right, well, have a good night.
You too. Is everybody all right? What's going on? You guys have what's up?
Yo.
All right, what's up?
Okay. 3 questions. 1, are we allowed to use a graphing calculator?
Of course.
Okay. 2, what time do I tell ARC? Because they just asked me right now what time I am supposed to be taking the exam.
Oh yeah, because they're probably not around this late. So you could either take it earlier that same day or the next day, whatever works best for them.
Okay. Okay, I'll let them know.
Okay.
And then my 3rd question. The exam is chapters 1 through 6, right?
Yes.
Or is it 1 through 7?
1 through 6. Yeah, I
Okay.
wouldn't include this trick stuff on there because we're just doing it now. Yeah. So it's 1 through
Okay.
6. Yeah.
All right. Thank you. Have a good day.
All right. You too. All right. I'm headed out.